This talk will be on the paper Almost Optimal PAC Learning for K-means, and it is joint work with us at Cohen-Addad and Lattanzi. The problem that we're looking at, or the setting that we're looking at, is PAC learning. In PAC learning, we're given distribution, and we want to learn something of the distribution, typically a function, and most commonly we want to find a minimizer over all possible functions that we're considering. What kind of functions we will consider throughout this talk will be given on the next slide. Now, the issue with finding a minimizer over all functions that we have is that we do not have access to the distribution. What we have access to are n independent samples S. And what we can do, for example, is compute the empirical optimum on the samples denoted by CS. What we're now interested in is how good does the empirical optimum compare to the true optimum. So specifically, we want to take a look at the excess risk, which is the difference between the performance of the distribution on the empirical optimum minus the performance on the distribution on the true optimum. And we would like to know how quickly the excess risk decreases as a function of problem parameters, and more importantly, as a function of the sample size. So ideally, we would like this to go to 0 when n tends to infinity. And what we're trying to study here is how quickly this happens. The problem that we're looking at today is the K-means problem. So the familiar formulation of the K-means problem is that we're given a bunch of points, and we want to place K-centers in space such that the sum of squared Euclidean distances of every point to its closest center is minimized. In the statistical setting for a distribution, it is basically the same problem, except that now we are trying to minimize the expectation over a random point drawn from that distribution. So this integral here, this is just the expected cost for a given candidate solution C. And the optimal K-center clustering with respect to the K-means function is the one that minimizes this expectation. So what is known for this problem? How quickly does the excess risk converge to 0? Well, in 1994, there's obviously a lot more results out here. This is just a small sample, but they are somewhat notable for reasons that we will see throughout this talk. So in 1994, Linda, Lugosi, and Ziegler managed to show a convergence rate of the order of square root KD over N. The dependency on K is optimal due to this lower bound over here, so you cannot do better than square root K over N, at least in high dimensions. The dependency on D, well, it is affordable if the dimensions are constant, but in high dimensions, it turns out to not be necessary, as proven by this next result here by Biao, De Broglie, and Lugosi, who managed to replace a dependency on D with a dependency on K. In 2016, Pfefferman, Mitter, and Narayanan managed to obtain a breakthrough of sorts, where they eliminated excess dependencies on K and the dependency on D at the cost of a logarithmic dependency in N. So they managed to prove essentially a linear convergence rate in terms of square root K and N, with only a slight loss in parameters in terms of these log factors here. This was further improved in 2021 by Apat and Catoni, who managed to improve some of these log factors. So they got rid of one log factor entirely, replaced another one with log K, and slightly improved the remaining two dependencies by obtaining log N over K. And this is also where the state of the art got stuck. So there's this bound here actually turns out to be fairly natural with the technique that everyone was using up to this point. And what we managed to do was break through this barrier. So we obtained a convergence rate of the order of square root K log K over N. So this has an optimal dependency in N and no dependency in D and a nearly optimal dependency in K. So the only non-optimal factor is this log K factor over here. Okay, so we will see how these various bounds came into place by giving a hint of the analysis as to what went into achieving these bounds leading up to our result, and then how we also overcame the limitations faced by previous results. So recall, we wanted to get a bound on this excess risk. We're only going to look at the expected SS risks throughout this talk, but we could also easily ask the same question for high probability, and there exist known ways to get from expectation to high probability. And it is difficult to relate these two quantities directly. So to compare the performance of the empirical optimum to the true optimum. So we're going to take a slight detour by considering the cost of a given solution on the samples, which is defined to be the normal k-means cost with this 1 over n normalization term. And now we're going to show that the cost on the sample is going to be tightly concentrated around its expectation, which is the cost on the distribution. So if this difference here is small for all possible candidate solutions, then we also know that the excess risk is small because the sample optimum cannot become too much more expensive, and the true optimum cannot become too much more expensive, and the sample optimum cannot become too much more cheap. Okay. And the starting point that we might ask is what happens for a single arbitrary but fixed solution? And in this case, standard concentration inequalities show that the difference between the sample cost and the true cost is going to be of the order of square root 1 over n. So for a single solution, we are already in good shape. What we now have to do is understand how much resources we have to expend to extend this to all solutions. So before we do that, we're going to use one nice trick from high-dimensional probability, where it allows us to, instead of bounding this quantity over here, so the expected maximum difference between sample cost and true cost, by way of a quantity known as the Gaussian complexity. So here we're trying to bound the deviation of the cost around its expectation. And if we take the inner product of the cost of all of the points in the sample with a Gaussian vector, so these are just going to be standard Gaussian variables, it allows us to study the concentration of this random process here around 0. So instead of looking at concentration around the expectation, we're now looking at the concentration around 0. And we do this by multiplying all of the random variables with associated Gaussians. This here is known as the Gaussian complexity. You can also use Rademachers instead. There are numerous technical reasons for doing this as well, but it will also simplify the presentation somewhat. Okay. So when trying to apply a union bound, first thing that we can note is that there are infinitely many solutions. So a naive union bound will not work. We cannot just enumerate all possible candidate choices of centers. We have to somehow find a more efficient way of counting them. And one efficient way of doing this is by way of discretizing candidate solutions. So if we're given such a candidate center indicated by this blue point right here, we can now throw a grid or some form of discretization over the set of solutions that we want to consider, and snap this candidate solution to the closest point in the discretization. So specifically, the type of guarantee that we're after is that of an epsilon net of the unit Euclidean sphere. So an epsilon net has the guarantee that for any candidate point, there exists a point in the epsilon net such that the Euclidean distance is at most gamma, and the size of such a net is exponential in d log gamma to the minus 1. The way that we now obtain a net analog for clustering is given a candidate set of K centers, capital C, to apply this discretization idea for each center individually. So this point here is now represented by this center. This point here is represented by this center. The assignment does not have to stay the same. So for example, if the closest center now moved to over here, then the difference in cost will still be obeyed by this gamma term, even if the assignments are not respected are not identical to the ones that were given by the dark blue solution. Okay. So let's see what the simple net construction does for the excess risk question. So we are building this net of solutions n gamma that we obtain by composing the epsilon net of the unit sphere k times. This gives us a total net of size that is exponential in kd log gamma to the minus 1. And now for every candidate solution, we know that it is represented by some solution C prime, where the difference in cost is at most gamma. Now you can set gamma any way that you want and apply a union bound over all possible candidate solutions in your net. This gives you a square root log of net size over n because the variance is constant, plus this loss in the discretization, plus this loss gamma here. And if you now set gamma to be of the order square root 1 over n, you get this overall loss, which is almost the result that we've seen earlier, except for this log n factor over here. So I'm not going to be too concerned with this additional log n factor. What we're going to study first and foremost is how to get rid of the dependency on D. So a natural way to try to improve this, this type of analysis is to use a form of dimension reduction when constructing this initial net. So there was no reason really to use a epsilon net of a high dimensional sphere. We can also first apply a suitable dimension reduction that preserves the k-means problem in some sense, and then do a net construction in the dimension reduced space. So let's see what happens. So recall we want this guarantee up here, so the k-means cost for any point has to be the same on the candidate solution and the approximating solution. And it turns out that if we apply a form of Johnson-Lindenstrauss dimension reduction, a form of Johnson-Lindenstrauss transform with a target dimension of gamma to the minus 1 log n, then we preserve this cost here up to an additive error of gamma. So replacing D with the new target dimension gamma to the minus 2 log n results in this net size right here. And if we now set gamma to be of the order of 4th root k over n, and doing the same analysis from the slide before, we obtain this concentration. So we get square root k times gamma to the minus 2 log n log gamma to the minus 1 over n plus gamma. And this actually, in some way, may seem a lot worse than the square root kd over n term that we had before, because now the convergence rate is of the order of 4th root of k over n, if we ignore the log factors. So strangely enough, even though it seems like we got rid of the dependency on D, the convergence rate did suffer. So in what follows, we'll see a very powerful technique for avoiding this loss, and this is also leading up to the state-of-the-art results for bounding the excess risk for the k-means problem. Okay, so the idea is that instead of using one single dimension reduction to construct a net, we will find a nested sequence of nets for different choices of granularity. So let this black point here indicate a candidate center of some target solution. We first will approximate it very coarsely by way of this candidate solution, and then subsequently take more refined approximations, which would now be, for instance, this one, and then this one, and so on and so forth. So the idea, instead of trying to get a bound on the entire set of solutions all in one go, we're now first going to bound the set of solutions indicated here by this red solution, the set of solutions indicated by the difference between the red and the green solutions, the difference between the blue and the green solutions, and then finally the difference between the black and the green solutions. So if you add this all together, then it amounts to the same thing. And instead of keeping track of this quantity here, we're going to keep track of the increments. That is the general idea behind what is known as the chaining technique. So specifically, we're going to choose gamma to be decreasing powers of 2, so 1, 1/2, 1/4, and so on and so forth. Then we know that the net sizes that we're looking at are going to be obtained by the Cartesian product of the nets of various granularities. The Cartesian product of the net size of the Cartesian product is not significantly different from the net size of just one of the two, and that is using the net that we already had of the order of exponential in 2 to the 2i, k log n log to the 2i. So this 2 to the 2i, that is the important term here, and that came as a function of the granularity gamma that we now parameterized by various powers of 2. Okay. Now we also know, and this is where looking at Gaussians becomes particularly useful, that if we fix the sample, then this inner product here is actually a Gaussian random variable, right? So sums of Gaussians are also Gaussian, and moreover, we know what the variance is. So the variance here, given that the size of the or the magnitude of differences here decreases by the order of 2 to the minus I, the variance becomes of the order of 2 to the minus 2I. Okay, so if we now combine everything, take a union bound over this, the variance is 2 to the minus 2I times a log of the total number of increments, so total log of the Cartesian product divided by n. And this results in this term right here, square root of 2 to the minus 2I, k times 2 to the 2I log n times I over n. We could cancel this out, but I'm going to leave it here because it will highlight the difference in approaches that we will see later. Okay, so now we apply this idea for all possible increments. And when applying this idea for all possible increments, for all links in the chain, if you will, you're going to sum up these differences here for all values of I. And then we're going to end up at, at this sum over here, which is the sum of I equals 0 up to some highest degree of accuracy, square root of 2 to the minus 2I times k times 2 to the 2I log n times I over n. You now set gamma appropriately, and in this case, we end up at a bound that is of the order of square root k log to the 4n over n, which recovers the result by Pfefferman, Mitter, and Narayanan. Okay. So why is the state-of-the-art stuck at this stage? Well, we have these nets of the side that are exponential in 2 to the 2i, and this is unavoidable if you are using Johnson-Linden Strauss, right? So the dependency on the accuracy that is tight for Johnson-Linden Strauss. You cannot really do any better. And in this case, we ended up at this sum right here. So the 2 to the minus 2i, which is the decrease in variance from one link in the chain to the next, that was countered with an increase in the net size. So this was a delicate balancing act that allowed us to cancel out things, but it still means that we're going to be left with the sum of all of these increments, which is where the log n over k comes from. Now this I you can get rid of if you're trying really hard, and the log n can be replaced by a slightly better variant of the Johnson-Linden Strauss lemma where you don't have to preserve the cost of all pairwise distances, so that gives you a log k. But other than that, if you're now looking to use Johnson-Linden Strauss, you're stuck at this bound. It's not really, at least if you only use a Johnson-Linden Strauss transform to obtain a net, it's not really possible to do better than this. And this is also the bound by Appert and Cantoni once you move this log n over k term inside. Our goal will be to construct nets of this size. So notice the difference compared to the Johnson-Linden Strauss construction, which is of the order 2 to the 2i. We are going to construct nets of the order of 2 to the I. And in this case, notice that now this sum here becomes a geometric series, which means that if we're now adding up all of these increments, we're no longer going to be losing this log n factor. Instead, it will just fade away to a factor of square root k log n over n. Right? So we actually get a very a far better control over this random process by constructing significantly better nets than what an application of most state-of-the-art dimension reductions would allow us in this case. Right. So how do we do it? Because Johnson-Linden Strauss turns out to be optimal for the type of guarantee that we're looking for. So we have to do something different. And the important observation or the important insight that we have throughout our work that allows us to overcome what Johnson-Linden Strauss is limited by is that we are only aiming to characterize optimal or nearly optimal solutions. And we will see how this is reflected in the analysis in a short while. Whereas Johnson-Linden Strauss, in some sense, overshoots by trying to preserve everything. And when trying to characterize only optimal or nearly optimal solutions, we actually managed to show that there exists something akin to a dimensional reduction where the target dimension is going to be of the order gamma to the -1 as opposed to gamma to the -2. So the key takeaway here that in some sense, so this is not a strong separation, but in some sense we're able to show that the convergence for nearly optimal solutions is a fair bit faster than convergence for arbitrary solutions. That is how we overcome the limitations of Johnson-Litten-Strauss. So if you're trying to do a net-based analysis, then Johnson-Litten-Strauss for arbitrary solutions is tight, but it also loses in terms of factors. We are using a net-based analysis, and using this net-based analysis, the rate of convergence is actually faster for solutions that are sufficiently good. The way that the main additional ingredient that we use in order to obtain our net construction is based on this following identity that is extremely popular throughout k-means literature. So it says that when you are taking the sum of square distances of any point set to a candidate solution C, that you can decompose this cost here as the sum of square distances of all of the points to the mean plus the number of points times the square distance between me and the candidate solution C. And as a consequence of this identity, if you now sample a few of these points, sample a few of these green points, and take the empirical mean on the sample, you can actually show that on expectation, the distance between the empirical mean and the true mean squared is the average one means cost times 1 over S. So what does this imply? Well, it implies that if we set the sample to be of the order gamma to the -1, we get a candidate mean that is epsilon approximate. So the distance between the true mean and the sample mean is going to be at most gamma because the average cost in the unit sphere is at most 1. And now the net for this one candidate solution is going to be of the order n choose gamma to the -1, which is roughly e to the gamma -1 log n. And you're going to now compose this for all candidate K solutions. There is a problem though. So by itself, this already looks very promising because it has this nice gamma to the -1, but there is a problem because it is not accurate enough. We are not interested only in getting a candidate mean that is close to the true mean. We also need that this candidate mean is close in terms of the cost for any other given point. And unfortunately, this guarantee only implies that the cost is close up to a square root gamma, whereas we need an actual gamma term here. So how do we manage to improve this? So first, we obtain candidate means that are somewhat close to gamma, again by just taking this enumeration over gamma to the -1 many points. And then we actually do a Johnson-Litten-Strauss dimension reduction where we explore the space around this, this candidate mean mu hat. But we don't have to do this to a very precise degree. So the nice thing now is that we only need an additive error of square root of gamma because these two errors, so the gamma coming from this term here and the gamma coming from Johnson-Litten-Strauss, it turns out that with a very careful analysis, you can argue that they multiply instead of adding up. And in this case, it is actually enough to aim for a target dimension of the order of square root gamma. So now the overall net size is going to be for every candidate solution this enumeration by means, which is n choose gamma to the -1 times the target dimension of the Johnson-Litten-Strauss dimension reduction with this refined precision of the order of square root gamma to the -1, and you compose this for all k clusters. So you obtain an overall net size of 2 to the k times gamma to the -1 log n as desired. Okay. So what are the takeaway? What were the takeaway messages from this talk? So we saw a simpler analysis of an improved convergence rate of the order of square root k log n over n. For the full square root k log k over n rate, you need a few additional ideas that sparsify your input, and those techniques may be of independent interest in areas where sparsification ideas come into play, such as corset research. In terms of open questions, there are basically, two main ones that I'd like to mention. So the obvious one is the square root log k factor necessary, yes or no? I personally do not have a very strong opinion. It is difficult to improve the lower bound, and we also so far did not manage to improve the upper bound any further. What is a slightly more generalist view on this is which other problems do not require the full power of the Johnson-Linton-Strauss transform. So one might ask what happens to related problems such as k-median, and for k-median, our techniques indeed do not go through. So it would be exciting to see other problems that exhibit a similar characteristic to the one that we utilized here. So where you can get away with weaker variants of Johnson-Linton-Strauss transforms to obtain better dimension reduction better dimension reduction methods or better generalization bounds. And that's it. Thank you for your attention.